exciting edition of PC Voyage. I'm Diana McLean.
And I'm Keith Davis.
And today we're at the University of Massachusetts at the
Letterly Engineering
Research Graduate Center.
That's exactly what I said.
Yes, and we're going to be speaking with Rod Gruppen and his group of students working on robotics technology.
That's right. And it's in that building right behind us, isn't it?
That building right there.
The Letterly Tower. And what are we going to see up there today now? What do you think?
Oh, we're going to see all sorts of things, including how a PC controls robots. We're going to see quite a few different robots also.
Yeah, and we're also going to see what they're doing up there with big computers and how they're advancing the science of robotics. And we'll see the results of all their work in a few years and different things, I'm sure.
It's going to be quite exciting. Join us.
That's right. Hey, how do you like the weather today, Diana?
Oh, it's a little windy.
Did you miss all the snow? Today's the first day you can look around and not see a pile of snow anywhere.
Well, you know, we skiers love that snow.
Well, you're out of luck now.
Okay.
Right.
I'll just have to travel north then.
Well, it's still pretty cold outside, so let's go inside and see what's going on with robotics.
Let's go in. Can't wait.
All right. You do the interviews and I'll run the camera. How about that?
Here, Today we're at the University of Massachusetts at the Lab for Perceptual Robots, and we're here with Rod Gruppen. Hi, Rod. How are you today?
Good, thanks.
That's great. Now, let's see what we got here. Look at all that, all those robots back there. That's great.
Yeah,
Tell
we
us
have
about what you do.
a great variety of robots here. Our basic philosophy is we are trying to generate technology which allows robots to function autonomously in complex worlds. Consequently, as you can see in the background here, on complicated robot systems with multi-fingered hands, we have mobile platforms, we have robots that see, feel, and in the future will hear their environment. We're trying to address lots of different fields. There, as you know, robots that explore underwater. They're building robots that explore in space. There is, in the future, going to be a desire to put robot technology in households and to have them as assistants. We're also addressing technologies that are useful to act as rehabilitation devices for physically challenged people.
Well, that's very good.
So a lot of the technology in this lab is related to how you can turn a robot on in an unstructured world and have it interpret what it sees and hears and feels in the world and generate motor actions to accomplish some kinds of tasks.
Would someone consider this part of artificial intelligence, or?
Yes, what we're doing is extremely relevant to the study of intelligence and to the human mind. And the way that a robot moves around and interacts with its world is, in fact, one of the most difficult intelligence problems. Playing chess, it seems, turns out to be relatively easy. But actually making a robot move around and not bump into things or pick up objects without dropping them is a much more difficult task. Just the fact that humans do it so well does not really suggest how difficult the problem really might be.
Now, what type of background do the people in this lab have to work on these robots and develop ways for them to do these procedures?
Most of the people in the lab these days have very strong sound computer science backgrounds as well as engineering disciplines. I myself have studied physics and mechanical engineering and computer science, and most of the people in the lab have that kind of a very strong physical science background as well as computer science. The lab, fundamentally, we're working on problems with information technology, how a robot can use the information it can extract from the environment in a useful way to perform task-oriented operations. But in order to do that, we really need to have very sound physical sciences, kinematics, strength of materials, control theory, that kind of thing as well.
All engineering.
Lots of engineering and information technology on top of that.
And how does it go as far as the computer science part? What type of things do you use? What kind of programming do you do?
Most of the programming we do in our lab is in C, in distributed environments. We have networks throughout the lab, as well as networks of controllers for our robots.
Okay, so what other things are we going to see today while we're here at the lab?
Well, today I think we'll be able to show you examples of robots which use sensors related to finding positions and forces, and learn how to incorporate that information with higher and higher skill levels over time. We'll be showing you robots that use motor control primitives derived from neuroscience to do reaching and grasping and manipulation tasks. We have robots here that are legged platforms that we're now building in order to walk in robust ways across irregular terrain. We also have robots which are wheeled mobile vehicles that use sonar arrays to try to interpret their world and move about in a purposeful but safe manner. Let me see what else we got laying around here. We have a head, a robot.
Just about everything, huh?
We have a robot head that allows a stereo pair to be controlled in a coordinated fashion so that you can extract depth and models of the world, just like a human uses binocular vision to interpret the visual scenes around them.
Well, you name the sense, and you got a robot to cover that, huh?
We also have these little microphones on every workstation where each workstation can act as a little hearing device which interprets the acoustic signature of the world, and by spatially arranging them in a spatial array like this, we can localize sounds and determine what made the sound. And so this room is really an instrumented room. As you can see, there's a camera up in the ceiling over here that just tries to look around. The room is instrumented. It gathers information from what's going on in the room, tries to correlate all of that. Eventually, we'll have all of that fused in a kind of a global representation of what's going on in the room. So it'll be aware of what the room's contents are doing.
Oh, wow. Well, right now we're going to take a break, and we'll come back and see a few more examples of this great job you guys are doing here at UMass. So Rod, what are we going to be doing now?
Well, there are several components of any autonomous robot task. Any robot, whether it be a mobile robot or a hand-arm system as we see in the background, needs to be able to move in a collision-free manner in its environment. That we refer to as the navigation task. Robots are dangerous, so they must be able to get from point A to point B without running into things. We also have a great deal of work going on how to coordinate multiple robots. When a hand is doing grasping, it has to coordinate multiple fingers so that they effectively complement one another and produce stable grasps, for instance. And we'll see some examples of that. In addition to that, when you're working with a hand, we talked about the vision problem. There's also a contact localization problem, which is fundamentally making a robot have the ability to see and feel. We also do in this laboratory, once we have these component technologies kind of giving some basic level of competence to the robot system, we need to be able to acquire skill over time and to become better and better at some motor tasks. And that's the area of learning, which is an active area of research in our lab. And so if you like, we can go around and talk to the people in our lab that do that work and find out exactly what they're doing.
Yeah, let's do that. Who are we going to talk to first? Rod, who is this that you're going to introduce to us?
Well, Chris Connolly is the person in our lab who is working on navigation, collision-free path planning, central problem to almost every robotics application. So Chris, can you describe what you do?
Can you describe it?
Basically, the idea is to get the robot to figure out how to get from where it is now to some other place. So what we'd like to be able to do is just point to a spot and say, go here, without hitting anything. And the way we do that is we get visual information or maybe some sonar information to get an idea of where obstacles are in the room or in the workspace. And then the robot programs its own path from wherever it is now to some goal position. And that's the basic idea. Yeah.
Oh, great. Thank you for telling me. Now let's go on to our next member of this team. Now, what is that I'm circling around?
This is our mobile platform. An application of some of the work Chris does is related to how to get this thing to roll around in this room without running into the people in the chairs.
Aha. That sounds like a lot of fun.
This is a, as you can tell, this is under construction. But it uses this array of 24 sonar, very similar to the ones that cameras use to auto-range for focus. Shoots a little ping off in this panoramic view and tries to determine where obstacles are and develops something of a map of its world that can then be used as the boundary conditions for Chris Connolly's navigation work.
Oh, wow. Very impressive. And who is this?
Manfred Huber, my name, and I'm a grad student here too. And I was working mainly on contact localization and in the last time on manipulation tasks for the robot hand.
And could you give a simple example of that to our viewers?
Well, we were coordinating the 4 fingers to rotate a can and to screw in light bulbs, using basically the same controllers that we're using to pick up objects. So you always want to keep the object in your hand, and that's where you use the grasping and everything.
A light bulb seems like a pretty tricky thing to try a robot on. Why did you choose that particular object?
Well, it is, I don't know, mainly Rod came up with this idea of this task of screwing in a light bulb. It's something that has some relation to a real-world task that you would actually do. Well, I mean, rotating a can in air doesn't necessarily have to be that much. So that's how we came up with that task.
It's really neat. Thanks. Who else is left?
Jefferson Coelho is working on controllers for trying to figure out how to coordinate the action of multiple fingers.
Come on over, Jefferson.
Jefferson's also a grad student in our department. He can give you a little brief overview of what he's working on.
Yes, one of the hard aspects of grasping is to convince people that this is really a very hard problem. And it involves coordination of multiple fingers, and you have many tasks that you must address. Screwing light bulbs, reaching for objects and assembling them into other objects, basically. And it's a very rich domain, and I'm very happy to work here.
Well, that's great. I'm so glad for you. So, Rod, you going to come back over here in the picture?
Vijay Gulpalli is the last person we have here that we can talk about some technology. Vijay works, once you give a robot this kind of basic set of competencies, now can you string them together in a way that causes the robot to execute these in a skillful fashion? Vijay's the learning person, the central learning person in the lab, and he can describe what he's been doing.
And I heard that you do this on PCs, or is that something else that you do?
That's right. We did some of this skill acquisition work using a PC. The problem we looked at was peg-in-hole insertion, which is an assembly operation that's very frequently used in automated assembly systems and factories and so on. The idea here was that we'd give the robot some kind of basic ability to do a task, but because we as humans cannot really tell what the robot's sensory capabilities are, what kind of an image it's getting of the world, and what kinds of uncertainties there are in that feedback that it gets from the world. What we wanted the robot to do is to actually perform the task in the world, use the actual sensory feedback that it gets, and try to do better and better. So the idea of a skill is that you want to perform a task repeatedly and get better and better at it. And so we thought that there was a definite role for learning in this situation. And we tried that on peg-in-hole insertions, which, as you can probably imagine, is a very skillful task where you want to put a peg into a hole without jamming it, without damaging the parts by applying too much force and things like that.
Wow, that seems pretty tricky also. Now, can you show us exactly what's on your screen, or is that does that have to do with the robots?
Well, I was going to show you the robot first, describe what it can do and how we use the PC to control it. And then
Well, that sounds wonderful.
so what we have here is the Zebra Zero robot that has 6 degrees of freedom. It is equipped with joint position sensors that can tell you where each of the joints of the robot are positioned. And it also has a 6 degree of freedom force sensor here that tells you the forces and moments that are applied to the tip, the grasp.
Let me get over here so we can get a better view of this. Okay.
Now, all the feedback that you can get from the robot is passed through this set of cables at the back here to this PC. This PC has a board plugged in which has motor controllers and A to D converters that convert the sensory feedback into signals that the PC can understand. This PC also has some kind of software that we can run to control the robot. I'll run something here just to show you what it does. This software has been written in Quick Basic, which is sort of convenient for developmental purposes because you can actually write some program and then have it run immediately to see how it performs. And then you can go back and change the program if you want. The program that we have here allows you to, for example, check what the force sensor output is. I'm moving this thing out from the nest. This is the force sensor here. I'm applying forces on this sensor, and the screen shows you what those forces are in these bar graphs. So as I push around, you can see these things changing.
It's very sensitive, isn't it?
It is very sensitive, and it is useful because, especially as I was describing, if you're doing things like interacting with the world, you want to be able to sense how much forces you're applying on objects in the world. I'm going to run the program which is going to bring this robot out of the nest and move it around just to show you the kinds of motions that the robot can do.
Great.
This is what's known as a dead man switch. If I hit this switch here, it cuts off the power. This is just to ensure that in case something goes wrong, we can turn the robot, kill the robot dead. And
just in case it comes after us, huh?
right. So here we go.
Wow, this is exciting.
So what the robot is doing now is trying to figure out where this endpoint is in the world by pressing it against this aluminum plate, which is called a nest. So it pulls itself into the nest, applies a certain amount of force, and then decides that, okay, that is its home position. And based on that position, it decides what it can.
Oh, wow, look at it go.
So now it's moving, it's each of the degrees of freedom. So you saw the first one was the base, the second one is at the shoulder, the elbow, and it can rotate at the wrist in 2 different directions. Well, actually 3. It's a 3-axis wrist, so it can rotate the last one too.
Boy, it's amazing to see all the different ways that you can get it to move.
So that was a basic demonstration of the capabilities of the robot. Now we want to use the robot to do things in the world. And one of the things, as I said, was to do peg-and-hole insertions. Mm-hmm. And the way we have it set up right now is that we have a controller that is specifying this task of peg-and-hole insertion that sends commands to the PC. The PC then takes those commands and interprets them and sends appropriate robot control commands to the robot itself, which drives the motors in the robot and makes it to do the specified task.
How long does it take for the computer to give the directions to the robot?
Well, right now we have it hooked up as a direct line, so it's practically instantaneous. Mm-hmm. And you can control how fast the robot responds and so on, just so that you can make sure you're not going to hurt the robot or hurt anybody in the environment. And you can monitor the forces that it's sensing at a very high rate. So it's not it's not difficult to sense what the robot is doing or to give it commands. What's the difficult part is to determine what commands to give it so that it can perform the task that you want to do. And that's where we're trying to use several techniques, robot programming and learning techniques to do that.
How difficult or time-consuming is it for the robot to change the order of tasks, say rotating as opposed to translating down to the table?
Well, as you
The
saw,
engineering terms.
well, there are some basic capabilities that we saw just now. So all those capabilities can be combined in arbitrary fashions. So you could have the wrist rotating while the elbow is moving, opening out or closing down. So all those at that level, it's fairly easy to do. You just specify the joint positions that you want the robot to go to, and it'll go to that.
So it's a matter of minutes to be able to change that?
No,
not
seconds.
not in seconds. Oh.
I could just. The robot comes with this language that allows you to specify what joint positions you want it to go to, and then it'll go to those positions. So it's not a difficult thing to do that. The difficult thing, as I said, is that suppose you want to insert that peg in that hole, what would be the appropriate joint positions that you should tell the robot to go to so that you successfully achieve that task? And that's where all this robot programming comes in. And that is the hard part, developing those programs, so that you can repeatedly, for example, insert pegs in holes without failures, without jamming, without exerting too much forces on the robot or on the environment. And that's the work that we do.
That sounds like really exciting work. It sounds like a lot of fun and quite a challenge to get that to develop into the proper procedures.
It is. And traditional roboticists have tried to program these intelligence into their systems. But I think we're doing something, and other people too are investigating this approach. But our approach is to develop a controller that does the best it can, and then add learning on top of it to refine it, to make that control a skillful control, so that the robots actually perform much like human beings in complicated tasks.
So how do you like that stuff? I think it's great. And are we going to finish up with the show now? Oh, I'd like to, we got to cut now so that we can go to our address. If you have any questions or comments about the show, don't hesitate to write in. And we'll be looking forward to hearing from you.
Well, here we have some code that actually does the robot controls that you saw just now. The code is written in Quick Basic, and it consists of simple commands that you can issue to the robot to have it do various things. For example, going down here, suppose I wanted the base, the first joint of the robot to move by 45 degrees. There is this command that I can give it. It says single joint move, SJ move, joint 1 by 45 degrees. And I can move it around back by minus 45 and so on. I can move other joints, 2, 3, 4, and so on. And the robot would just execute those commands because of the board in there, the motor control board that drives the robot to interpret those commands.
Wow, that's neat. It's much easier to look at it that way and see how it works.
This is really convenient also because the Quick Basic environment allows you to go into what is called an immediate execution window, and I could get in there and do SJ move. And I could issue this command in immediate execution mode and have the robot execute it.
That's amazing, huh? Thank you very much for talking about that. That's great interest to our viewers who are PC fanatics like me. And now we're going to wrap up the show. Let's see, where's Rod? Well, we really enjoyed our trip today to UMass to see you guys in your perceptual robotic lab. And I want to thank you very much for having us here.
Thank you for coming.
So tell me, as far as the future goes, what do you see this work that you are all doing on these robots?
Well, some of the work that we're doing is already being used in manufacturing lines to guide the control of arc welders that are assembling automobiles and whatnot. It's used in automatic inspection for quality control. We imagine that some of the other technologies we're working on in our lab could hit the marketplace in a year or two as well. On the other hand, things like the hand controllers that we're working on may not be around for 10 or 12 years, but we'd like to see them a kind of a common household feature in the next several decades. So you never know, you might find this robot screwing in the light bulbs in your house one day.
Sounds pretty good. And thank you very much once again. Well, we're back outside now. I thought that was a terrific trip to see Rod Gruppen and his group working on those robots.
Rod Gruppen and his group, huh? I wonder if he has any groupies. Hi, Rod. And be careful where you park up here, by the way, everybody. But anyway,
That's another story.
What I really liked about that was...
what did you like about that?
The fact that if you had a PC at your house and you had a card you could put in your PC that could feed some cables out to a little robot, that you could write the program for it in BASIC. You had the program they had written in QBasic, and it was pretty extensive, the one they had, but any of the given commands to make the robot do something really weren't all that difficult, you know?
Well, for the basic functions, but I'm sure for the more advanced versions you would have to have a little background in that.
But, oh yeah, especially if you want to try to screw in a light bulb or something.
Oh my goodness, can you imagine not trying to break that?
I know I have a hard enough time as it is, so,
yes.
Well, someday we'll have a robot, like you said, doing that for us at our house, but...
I wouldn't mind.
No. But, we're up here at UMass, and we hope you enjoyed the show today.
And we'll see you next time on another PC Voyage.
I'm Keith Davis.
And I'm Diana McLean.
And away we go.